Hi, my name is Niranka Banerjee, and our paper is titled Output Sensitive Fault Tolerant Maximum Matching. This is a joint work with Manoj Gupta, Venkatesh, Raman, and Saket, Saurabh. So, first, let us start off with what is the model that we are working on in this paper. It is called the fault tolerant subgraph model. So, what is this model? Given a graph G, we will preprocess and store a subgraph H of G such that now when the adversary comes after that and let's say it deletes any f edges from both G and H, the goal is to preserve a specific property of G minus f in H minus f. And this property can be your favorite polynomial problem, let's say cuts or matchings, reachability, connectivity, any of the problems. The objective here has both an upper bound flavor and a lower bound flavor to it. For example, for the upper bound, we need to find out a subgraph H with as few edges as possible. But on the other hand, in the lower bound, we need to find out a subgraph and we need to show that a subgraph with very few edges does not exist. Just as a warm up, let's take the example of all pairs connectivity in undirected graphs in this model. And if the number of edges is edge faults is phi, that is 0, then we can see that H is nothing but a spanning forest and the size of H is around n. However, if one fault is introduced, then for the construction of H is the following. We first pick a spanning forest of G, insert it into H, then delete those edges from G. From the remaining edges, we pick another spanning forest and add it to H again. Notice that this construction of H is always robust to one edge fault. And the size of H is 2n. That said, now let us come into our results or what are the problems that we considered in our paper. We consider the problem of maximum matching on bipartite graphs and on general undirected unweighted graphs. These are for different values of faults we considered for different graphs. So a basic definition of maximum matching mu of a graph G is a maximum set of edges such that no two edges are adjacent to each other. And as for the fault tolerant definition of the same maximum matching problem, we say that a subgraph H of G is an alpha F fault tolerant maximum matching subgraph if it has the following property. For any set F of at most small f edges, vertices or edges in G, alpha of mu G minus F is the maximum matching value of the maximum matching in G minus F is less than equal to mu H minus F, which is the maximum matching value in the subgraph H minus F. And alpha here is the approximation factor. If alpha is 1, we are basically maintaining the exact matching. Otherwise, depending on the value of alpha, we maintain that approximation of matching in H minus F. As for previous results in the same problem, Asadi and Bernstein in SOSA 2019 showed that for any epsilon greater than 0, there exists a 2 by 3 minus epsilon, comma f fault tolerant matching subgraph of size order n plus f. Note here that 2 by 3 minus epsilon is the approximation value and f is the number of faults. Okay. In this paper, we initiate a study of 1, f fault tolerant matching subgraph. So what it means is we want to store the exact matching, and that is by 1. The approximation factor is 1. So we will, in this case, because we are just dealing with 1, f fault tolerant maximum matching subgraph, we will denote the subgraph simply as FFTMS. Next, let us come into why the output sensitive nature of our algorithm. What does it mean? So the point is, the problem of maximum matching has an omega n square lower bound on the size of the subgraph for quantities of f, for values of f greater than equal to 2. And let's see why. Let us take this graph, for example. This is actually a bipartite graph where A and C form one partition and B and D form the other partition. Now, the vertices in B and the vertices in C all have degree 1. there is an edge going from each of the AIs to BIs, each of the CIs to DIs, and there are edges going from all AIs to all DIs. If the number of vertices is totaling to n, then we can see that the number of edges in this graph is order n square because of all the edges from AI to DI. And the maximum matching size obviously is n by 2. For every AI BI, there is a matching, and for CI DI, there's a matching. Right? Now we can show that all edges from A to D should be there in any subgraph of G if we have to maintain the maximum matching size. And let us see why. Suppose not, and without loss of generality, let's say the edge A1D2, the red colored edge, is not there. Now the adversary may come and delete the edges A1B1 and C2D2. In which case, note that because this edge A1D2 is not there, the maximum matching value in the subgraph that we have maintained actually falls by 2. Whereas if this edge A1D2 was there, the maximum matching value would have actually fallen by only 1. So our subgraph in this case cannot maintain the maximum matching value. This shows that all the edges from AI to D, all the DIs or the DJs should be present, in which case there are omega n square edges in this graph. So this is what we say here, that therefore the size of G and H is the same and order n square edges are there. So now what do we do? Because n square is not a good enough bound, because we say that we cannot do anything better than actually keeping all the edges. There are such graphs that exist. Next, what we do is try to see if we parameterize a subgraph size H that we are maintaining, or the FTMS, by a maximum matching size. And then we will see what can happen. So this brings us to finally our results in this here. So firstly, we show that on bipartite graphs, there exists one FTMS for one edge fault with order mu G vertices and edges. And this we also show that this bound is tight. And this is for f equal to 1. Further on, for general graphs, we show that there exists FFTMS with at most f edge faults with order mu G squared plus mu G f edges and order mu G into f vertices. Again, we provide a matching lower bound of omega mu G square comma mu G f, max of mu G square comma mu G f edges and mu G f vertices for FTMS. But unfortunately, our lower bound only holds for f greater than equal to 2 and above. Okay. So for the purposes of this talk, we will concentrate only on the first result, which is that on bipartite graphs, there exists a one FTMS for one edge fault with order mu G vertices and edges. So let us see how we will go about constructing a subgraph. So now for the easy case, if an edge does not belong to the initial maximum matching mu G, there is nothing to do, as the fault of such an edge does not change the size of the maximum matching. So now let's come into the more difficult case, which is an edge A comma B, which belongs to the initial maximum matching. Now we need to know if there exists an augmenting path in G minus A comma B. That is, if the edge is faulty, then in the remaining graph, we need to know if there exists an augmenting path or not. Because if the augmenting path exists, then the maximum matching size will remain the same. If not, then the maximum matching size should reduce by 1. Okay. Now, augmenting paths can be of two different types. One is for a matched edge A comma B, which is the red edge here, there can be an augmenting path that starts from B and ends at A in G minus A comma B. Or there can be an augmenting path from either A or B to an unmatched vertex in G minus A comma B. Here I write unmatched as free vertices here. Or there is an augmenting path starting from B and then ending at again a free vertex in G minus AB. Right? So there can be two types of augmenting paths. Now let us look at the construction of our subgraph when we look at the first type of augmenting path, which is there is an augmenting path from B to A in G minus A comma B. So what is the strategy? First, we will convert an undirected graph, bipartite graph into a directed graph by a known construction, which is direct all the matched edges mu g from left to right and all the unmatched edges from right to left. After this forms a directed graph, and then what we'll do is essentially partition the graph into strongly connected components. How does this help us? So you see that the matched edges are from left to right, the unmatched edges are from right to left. Now notice that if there is an augmenting path starting from B and ending at A, then this entire construction would be basically a directed cycle, which means that this edge A comma B, this matched edge A comma B will be part of some strongly connected component. So this is what we state here, that if there is an augmenting path from B to A in G minus A comma B, then this path union A comma B is always part of some strongly connected component because it forms a directed alternating cycle. Hence, some partition will contain this path. This is basically our strategy. And let us look at the size bound for this. So we partition it into strongly connected components, and that is essentially our algorithm. Now, to bound the size, what we have essentially showed in the paper, and I'm not going into it in this particular talk, that for every matched edge that is part of the strongly connected component, there are at most 2 unmatched edges, or every matched edge can be charged to at most 2 unmatched edges in our construction. So the total number of edges that are in the construction is actually ordered mu g, if you realize. Right? Now, let us come into the second type of augmenting paths, which is there is an augmenting path starting from either A or B to an unmatched vertex in G minus A comma A, G minus A comma B, or there is an augmenting path, this should be A, and this is, or there is an augmenting path from B to an unmatched vertex in G minus A comma B. And this is basically the diagram. So what happens in this case? How do we bound the construction of H? Again, this is quite simple. The point is, if there exists an augmenting path that is starting, let's say P1 starting from B, and there is an augmenting path, let's say P2 starting from D to the same free or unmatched vertex, and P1 and P2 are not phi, then basically we are saying that the total length of both these augmenting paths is double the number of matched edges in P1 and P2. In other words, the number of unmatched edges and the number of matched edges are actually the same in this case. And why is that? Obviously, we can see that, let's say P1 was constructed first from D. Now, when P2 is constructed, all we have to do is to find out the first point of intersection starting from P2 and ending at P1, the first point of intersection, and the construction should only be taking the edges should only be added till that first point of intersection in P1, because we know that if those edges are added, we will by default get an augmenting path starting from B and ending at an unmatched vertex. This is essentially the main idea behind showing that the length of both these augmenting paths is double the number of matched edges. What we mean by this is the number of unmatched edge and the number of matched edges are the same when we are constructing this. And just extending this construction to all matched edges, we will get that if there is an augmenting path from a vertex, say A or B, to an unmatched vertex, we will be able to construct that. Again, I have already talked about this, that size bound in this construction, for every matched edge, we have at most 1 unmatched edge. Right? And thus we say that the total size of the constructed subgraph is ordered mu g. And this ends the proof for construction of one FDMS. Now, let us look at the lower bound, and we say that the lower bound is actually tight. So what we say is for any positive integer n, there exists a graph G is equal to V comma E on n vertices and a maximum matching mu G, whose one FDMS requires at least 3 mu G vertices and 2 mu G edges. Let's see how we do that. Now, this is again a simple proof. What we have is for every AI in partition A, there is either a matched edge to B, basically B2i minus 1, and there is an unmatched edge, which is this yellow dotted edges that are going to B2i. So A1, B1, A2, B3, and A3, B5 are the matched edges. Now, again, we can show that all the yellow dotted edges have to be there in our subgraph. And why is that? This is again a simple reasoning that suppose the adversary comes and deletes any of the matched edges. Now, in the original graph, if A1, B2 edge is not there, then the maximum matching size would have decreased by 1 if we had not kept this in the subgraph. But the actual matching size would still remain the same, because in the actual matching in the graph G, A1, B2 edge will always be there. This is basically the reasoning behind getting 3 mu G edges and 2 mu G vertices. So that's kind of it for the talk, and we will end with an open question in this area. So if we look at the overall contribution, we have proved tight bounds for f equal to 1 and bipartite graphs. And we have not covered it in this talk, but in the paper, we have also shown tight bounds for f greater than equal to 2 for general graphs. Now, the obvious open question that is remaining, and that would give us a complete understanding of exact matching in the fault tolerant subgraph model, is that if we can find out the size of a subgraph for f equal to 1 for general graphs. Thank you for listening to me.